Here we go. Welcome back. It's another week, and I've scared you down to 8, maybe 9, 10 people. 9, 10. That's a significant drop.
We're all going to use the
Oh my goodness. Well,
until it teaches us something.
I can't help you there. I can see why. I mean, we've been busy doing this forever. So, but we're going to keep doing this forever. So that's the way it goes. One thing I wanted to show you was, with respect to this class, the only class that you're in with me, homework number 2 was previously due this Friday. And that seems unrealistic that we're going to get through everything. And I don't want to hurry through certain things. I want to, like, teach you rather than, like, throw everything at you. So I've extended the deadline for homework 2 for another 2 weeks. October 3rd.
That's great.
Awesome.
I'm not exactly proficient. This homework system I use. Get that. It's clunky, as you know. It's not the best, although it's pretty cool that I think I told you backstory. My wife Lisa built it. She wrote it all in SAS, and so I'm trying to do everything working with it. So it's interacting with HTML. Hello. With all sorts of moving parts to it. So if there's something wrong when you try to submit, let me know, and I'll try to fix it. Ultimately, all the grades are kept in the database that I have, and so I can fix that. And it's not like a big system like Blackboard where if something screws up, you've got to get help. I'm the system administrator, so we can fix it. I did say that 3 of you have attempted the homework, or at least started the homework. That's great. But again, we're not through everything yet that you need to do. I think by the end of this week, we'll probably be everything where you need to kind of dive in and try to answer some of the questions. The homework is essentially, there's a data set that's real data, and you can do CFA with it. A couple places to do CFA. And again, the purpose of the homework is to get you to kind of see where the parts of output are that are important, because there's a lot of output that comes from Levon and all this. So that's that. Questions? Comments?
I have to clarify one thing. Last class I say there is a rounding error.
Mm-hmm.
Actually, it's not a rounding error. I didn't change the denominator of that covariance from n minus 1 to n.
Yeah, that happens. Yeah, no problem. No worries, it happens. If you get in a spot where you, and just on that note, thank you for asking last time, but couple things. Number one, I am doing the homeworks ahead of you. Actually, Lou and I are both doing them. So I sent Lou to take a look to see what the compatibility with Levon and M+ is, because all my homework's been done in M+. For this one, it was high. But then I work on it too, because invariably there were still 3 or 4 questions on this homework that you could easily get access to the answer in M+, but you can't easily get in Levon. So I thought, I'll change those questions. So I changed them. So I will say that I did every one of the questions, and I checked them, and that's why I was like, no, it's not a rounding error, because that. Now the next homework is going to be a little bit more of a hassle, not because of for anything for you, but for me, because of we're going to use CFA. It's like CFA with categorical data, IRT essentially. And wouldn't you know, that's where everybody's algorithm is not exactly spot on, right? So in that one, it's going to be a little bit, for whatever reason, for various reasons, not necessarily sloppy programming, but just different constraints for convergence and different ways of calculating certain things. So anyway, point being, if you're in a spot where you think, I'm getting this right, and you can't quite see it, try it to understand the problem well enough and to describe what you've done, then either shoot me or Lou an email, because we can help you troubleshoot it. And that's mainly because we've both done the homework probably a week before you started. So it's usually pretty fresh for us. And that's just not for you, Jihong, that's for everybody if you're in that spot, okay? I want you to try, because oftentimes the solution is there. The questions may not be worded exactly the way they need to be, or something may be omitted. That's certainly a mistake that we can make. But a lot of times, historically with the homework system, the first thing that people say is, well, there's a rounding error, and it's usually something that's not. So just think of it that way. How that goes. Okay. There. What else? Anything you want to think about? Talk about? Okay. Things are back to normal on campus. KU football is not playing well. We are trying to do our best. We're getting behind in class. I mean, things are just the way it normally is, right? So we left off last time starting to talk a little bit about model fit statistics, and we got into number of parameters. We got into where the model fit comes from and the sort of the philosophy of it. Do you remember where that was going last time? Sort of. What do you remember? You could pick one thing out of your mind from last class, tangential or otherwise. What do you remember? SRMR, not the be all and end all. That's right. What is SR? Smurmer. First of all, it's sort of a pronounceable series of letters, so it makes you think, oh, this is almost something I could use, but not quite. So let me grab this. Anybody else? What else do you remember? Oh, that's right. Yes. That conference is actually coming up in a couple weeks. I'll be going, well, I'll sort of be going to it. I'll be there enjoying the lack of, no, not enjoying actually. Actually, what I'll be doing is playing, chasing after my toddler who's coming with me, so.
But actually all the number of items and how that relates to the factor in your model.
That's great. Yeah, that's right. So we talked about to minimally identify a model. There are certain types of the word identification gets used a lot. And one thing I noticed as I was going through the slides is that we sort of just use the word blanketly, identification, which if you're coming in off of the street, you say identification, you're like, what are you, the police? Like, like I don't, I got my ID right here, right? Or something like that. With us, identification really means to make the model have a unique solution. There's certain things you have to do, right? Statistical identification means there's one unique solution. And in factor analysis, there's the identification based on the scale, right? You had to set the scale somehow for your factor. Something with the mean, something with the variance. The easiest one to remember is set the mean to 0, set the variance to 1. That sets the scale. The harder versions of that are when you're estimating the mean or the variance. You've got to set either an intercept to 0 or set one of the loadings to 0 or set some other constraint to either of those. That's scale identification. But then there were a minimum number of items that you needed to have to find the factor itself. And so when you have one factor by itself, you actually needed 3 items to have a just identified factor. Right? You needed 4 items to be able to actually test that hypothesis, whether that factor was doing a better job than just having the items and their correlations be represented themselves. Right.
Just a clarification, because I had a discussion last week or so about the difference between, because we discussed the idea the difference between the mean and the intercept. So the mean is the mean of the observed mean of the item itself.
So what we have to remember the data. We have to come up with a model that reproduces things about the data, and one of those is the mean, the observed mean itself. Yes.
And when we say the intercept, it's the latent.
The intercept is literally, so if you have an item like y1 for a subject, mu1 plus, let's say, lambda 1 times f for the subject plus error 1s, right? The intercept is literally the intercept of the regression line for that item.
So if you apply this formula, it would be like the intercept would be y minus lambda f.
Oh no, there's no y. So if you move y over here,
Yeah.
this whole thing would equal 0, right?
Then
No, what is an intercept in regression? What's that mean?
the conditional mean.
Zero.
That's right. The mean of the y whenever f is equal to 0. Right? So that's what the intercept represents. Right? And every variable we have in our equation, like even f right here, f for s, is going to have a mu for f plus an error for it. Right? What does this intercept represent? Well, there's no other predictors for it, so it has to be the mean of the variable. Right? So does that help a little bit?
Yeah, it's clear.
No.
But like now, if we compare it to the mean, it's mean.
That's right. What is that going to give you? So you've got y bar over here, right? Y bar 1, that's the mean of y. So if the mean of y is what we sometimes call in statistics the expectation of y. Right? So, and I'm doing this because we do have somebody who's doing math stat this year.
You gonna write me a moment generator?
Well, no, we're not going to have. We'll just generate the first moment here. This is actually called the first moment, and this is our first moment, really. Anyway, Jesse and the rest of you who want to figure this out, whenever you see something like this, y1s, you just pass the expectation through. So it's the expectation of mu1 plus the expectation of lambda 1 f, the subject, plus the expectation of error 1s. So okay, what is all this? The expectation of mu1 is a constant, so that's mu1. The expectation of this thing right here, lambda 1 is a constant, so we can pull it out times the expectation of f, bless you. And the expectation of error we set to 0 by definition, right? That's gone. So what we're saying is the mean for y is always going to be equal to the intercept for the item plus the loading for the item times the mean of f. Right? The expectation of f, I could replace this with mu f here. So now you can see with scale identification how the expectation matters, right? If you've identified your scale by setting the mean of the factor to 0, you've just effectively set the intercept for every item, the item mean. Right? If you've identified your scale by setting one of the intercepts to 0, like item 1's intercept to 0, then the mean for that item is going to come from the factor loading times the factor mean itself. But because what you're going to find is that you set one, with our 6-item example, if you set one of those intercepts to 0, you're estimating 5 other intercepts and 1 factor mean. You're still estimating 6 things that go to the mean. It'll perfectly reproduce the mean. Exactly. Now that gets into a bigger step. So when we talk about model fit, right here, the big picture of model fit, we always say the mean is often ignored because we perfectly estimate it. And that's true. Right? When we estimate all the intercepts, set the factor mean to 0, we get the means back in the intercepts. Right? So it doesn't contribute to model fit. But what if you sat there and thought, wait a minute, for whatever reason, I want to test whether or not my means are all equal for my items, or my intercepts are all equal for my items. Right? Well, there's nothing stopping you from setting a constraint so that all the intercepts are equal. And now you're in a situation where you might have misfit for the item mean, and it might contribute to model fit issues. Right? So there's ways it can reverberate through. Does that help?
Yeah. So it seems that we are talking about conditional. The mean is conditioned on the other parameters.
That's right.
And this, like the expected, like.
That's right.
But in the other, no, there is no condition. It's the mean when you have 0.
That's right. That's right. Yeah. I mean, effectively, the intercept either represents the mean if we set the factor mean to 0, or the mean of the item is given by something else. But so long as we only have one constraint on the means, or one constraint with respect to the intercepts, then we're going to get all of the other. We're going to get perfect fit there. Other questions? Okay. So getting back to model fit, the mean because the way we set up our default model is pretty much always estimated perfectly, so it doesn't contribute to model fit. The variance is also that case. If you wanted to switch up, have you seen the variance function before? For those of you who like expectations, I singled you out the last class. This is nothing.
No,
This
really,
is nothing different.
This is what we're covering in probability right now.
The expectation of x is sometimes called the mean. If we want to talk about the variance, it is the expected value of x minus the mean squared. Right? So it's another type of expectation. So what that ends up doing is it has its own algebra that goes along to it. There's a certain algebra that goes with all this, and what that algebra really comes from is from calculus. There's either a sum or an integral across the space of what the value of the variable can be. Blah, blah, blah. You don't need to know that. What you need to know is regular form here. The variance of y we can do a similar function for. We can put the variance function through here, and we can see when we assume that the factor and error are uncorrelated, there's no covariance between them. We know that mu is a constant. We know that constants don't change the variance. Right? It shifts the location, but it keeps the variance of the distribution the same. So what we end up getting when we do this, so long as we only make one constraint with respect to the variance, is either one factor loading set to 1 or the factor mean set to 1, we say the variance for each item is the factor loading squared times the variance for the factor plus the variance of error, which is our unique variance. But what that all goes into saying is that we perfectly reproduce the variances as well. So we know that we're getting the means spot on, we're getting the variance spot on, so the only place that we can be off are the covariances. And that's where we start to see the issues for model fit. So remember, yes?
So going back to this equation, we can say we explain it perfectly. Like we have a perfect factor indicator load or factor loading, and we know perfectly the variance of the factor. The error will be like 0, and if this is like across all the items, we would not be having like covariances between the items, theoretically speaking.
Right, yes. If the variances were down to 0, all the variances were 0, you'd have this degenerate solution where, yeah, and that, more often the case, the variances are, there's lots of room for that.
Yeah.
So really, when we look at our model, we talked about last time that there are 3 different models estimated, right? There's our model, there's the saturated model where we estimate all the covariance parameters, and then there's the independence model where all the covariances are set to 0. This is sort of the model of last resort. That's like, should I even bother continuing to look at my data? Right. So we see our output. When we started getting into global, that was M plus output. I left the M plus output in here, but I have the output that we're concerned with in the R part. And actually, let me get down here. There we go. You'll note that we talked about information criteria. We talked about the log likelihood. That's the sort of the peak, the likelihood function. That's where the good parts. That's where we want our numbers to be. We also talked about the scaling correction factor. This is something that is something called robust maximum likelihood. When you hear robust and you're not in statistics, what do you think of first? Yeah, that's what I was going with. Hardy, robust. Adjective for heavyset people too, right? Robust myself. I don't know why. It's something that helps us when we have not necessarily normal data, but we still have the assumption of continuous data, which is, to me, if you're going to take the 2, we're always breaking that continuous assumption in CFA. Like when we've done that, this isn't really going to help us a whole lot. But anyway, what that does is provides a rescaled log likelihood for what we do, and what we see here is here's our log likelihood. So we want to look under the robust column for everything we do. Again, the reason for that is if we had perfectly normal data, the robust column and the ML column would line up. So you're not penalized for looking at one versus the other. But here, what we see is this is a likelihood ratio test. It is comparing our model, right, with the saturated model. So our model is the null model. So essentially our null hypothesis is our model fits. alternative hypothesis is, well, the model doesn't fit. We'll just keep it simple. Right, but the two models for that are the null model, which is ours, H0, and H1, which is the saturated model. So all the models that we're going to come up with in this class, and when I say that, all the models that have a single class of people, so we're not doing a factor mixture model or something like that, will fit, we're nested within the saturated model. Okay. Okay. Question? Nope, sorry. Oh, sorry, no problem. So if you wanted to see where this model comes from, I'm going to go and scroll down a little bit. This next section of output on my code is the actual saturated model itself. So in Lavon, what we do with the saturated model is essentially this, right? We have this multivariate normal assumption for our data, so we need to go and specify Lavon to estimate all the means, all the variances, and all the covariances. Well, the means get estimated by this tilde1 function, right? So I put all my items with tilde1 by it. The variances are the double tilde where on each side the same variable appears. And the covariances are each item with every other item, and you don't have to put that in once. So item 1 with item 2, item 1 with item 3, 4, 5, and 6. Now I couldn't figure out the shorthand to make this go faster. Maybe you can. There probably is, but I had a deadline. I wanted to try to get this out. So I sort of just made something that works. There's probably more elegant ways of doing it. Have you heard that in math? Elegant. I think of all the words in English that we use. Robust, elegant. Like the things that you would never think applied to math, right? So in the business I'm in, like in the CFA biz, we talk about an elegant solution as one thing really, it looks just really nice, right? This may not be elegant code. Point of the matter is, though, when I estimate this, there's no factor there, but I'm estimating everything because how would you know that? Well, take a look right here. Our user model, H0, log likelihood, and our unrestricted model, H1, are identical. And when that happens, if we take a look at the number of parameters, 27 with 27, a model with the same number of parameters and the same log likelihood is an identical model. So it goes a step further than that. You have to have the same items and the same people. Right? You can't take a part of your data that has the same items, but not all the people. It won't be identical. So everything that we apply, the log likelihood is based on, is anchored to, tied to the number of people you have in the data set and the number of items you're using in a model.
So can you interpret that like when your null model and your saturated model are identical?
You basically have perfect model fit, or another way of putting it is your model is no different from having every mean, variance, and covariance for the data.
The data is perfectly normal then, right?
Mm-hmm. Not perfectly normal, but it's that the models are identical. So what I mean by that, for instance, if you ever do mediation analysis.
When you say robust and non-robust line up if your data are normal.
Oh, pardon me. Robust and non-robust do, but this is just the log likelihood. For whatever reason, they're not giving me the robust version. They're non-robust. They're giving me the same. I don't exactly know where that is coming from.
I thought the right was still the robust.
Yeah, the right is still robust, and I don't know why it's identical to the left because it's not guaranteed to be. But
is the left side the non-robust though?
This is the non-robust. But for whatever reason, the way I've specified this, they're not separating it. Like if you do this in M+, it would be different.
Lining up.
It's that the model itself.
Got it. Okay.
Where I'm talking about, what you're talking about there is this is the normal. You're right, Katie. This is normal, perfectly normal data. And what I'm saying is that shouldn't be in this case. It's not perfectly normal. I don't know why it is.
Okay.
But the direction I'm comparing is up and down. So because H0, and I'm only going to look at the robust side, even though they're the same. H0 is identical to H1. That means that the model you're fitting is identical to the saturated model. So think about this. What do the models mean? Like in this case, we know we're trying to replicate the saturated model, so I'm just trying to show you it. But there are cases in your life where you're going to see a saturated model. And one of those cases that comes up lots, like mediation analysis with 3 variables, right? If you've got, I think we call it X, M, and Y. This is our classic mediation setup. These are observed variables. X predicts the mediator predicts Y, X predicts Y. There are 3 variables there, and this has the perfect number of parameters to fit the saturated model. So what you're saying there when you do that is a couple things. In a measurement system, this is not a measurement model, right? This is just simultaneous regression. But for a measurement model, where we see this a lot, if we have a factor, we have 3 items. Well, this is y3, y2, y1. Like this. Sorry for my drawing. That fits perfectly. If it fits perfectly, it's like saying it's either this, or it's the case where this is like model 1. I have that same x1, or y1, y2, y3. We just had this right here. And I'm not drawing the eye of providence on there, but the means also go with it. These 2 models are indistinguishable. That's what it's saying, right? So in a measurement context, when you really believe there's a factor there, that's important. Because if you can substitute another model and get the same model fit, you weaken your argument for why that factor truly exists, right? It's not necessarily falsifiable. If we've observed data and it's perfect fitting, that's not weakening any argument. In fact, we're just trying to describe the patterns that we see in our observed data. We're not trying to say there's a factor of it. X, M, and Y are all observed. So we're not trying to infer a variable from it. We're just trying to see their patterns of relationships. We're trying to see exactly what the strength of the direct versus the indirect relationship of X on Y happens to be.
Like that.
Exactly. Yeah, she did.
So in order to be sure
Mhm.
that you have perfect model fit, then you look at the log likelihood
Mhm.
and also the number of parameters.
That's right.
For what we have here, then you would look at the robust side, where those 2 numbers are the same.
Mhm.
Then you see that the saturated model has 27 parameters. Would you have to go back and look at your null model
That's
to make
right.
sure that has 27?
That's exactly it.
Okay.
Yeah, that would be it. Or the other place where you can see it, you go up to your likelihood ratio test. You should see 0 degrees of freedom.
Okay.
Right? 0 degrees of freedom tells you number of total parameters, which come from the saturated model, minus your model.
Right.
If it's 0, that means you're at the saturated model. Yeah. So yeah, basically when you see zeros right up here for the likelihood ratio test, that means you are fitting perfectly. Number 1, you fit the data perfectly. So no argument about model fit. Model fit is no longer relevant. The question then becomes philosophical, right? If you're making a measurement argument, my philosophy is you really need to test that factor is there. You need to falsify it. This isn't falsifiable because you're saying these 2 are interchangeable.
So the expected variance covariance will exactly the same as the input variance covariance.
That's exactly right.
And residual variance will be zero.
That's exactly right. In fact, we can even show that because, oh shoot, come on. I'm looking in the wrong place, of course. Here, if I put the residual variance, there's a function called resid. I can show you what that looks like. This is the residual variance. This is the residual vector of means. This thing right here, this is the difference between what the model think the mean for each item is and y bar is for each item. And then the covariance spot, down the diagonal is the residual variance, and the off diagonal is the residual covariance. So when you see zeros here, we fit perfectly.
How often does this kind of situation happen?
It happens almost never when you're doing a measurement model and you have more than the minimum number of items that you have. So I'm telling you this, I'm going a little bit overboard on this because there are situations that occur in your life where you'll be trying to submit a paper and you'll be doing this up here, right? Which is effectively taking all these covariances and changing them into regression weights. Right? And I've seen editors and reviewers say, oh, I want to see the model fit statistics. They're perfect. It's saturated. Because that's the sort of their Rolodex of things to check. You can argue this is fine, right? There's other situations in life where you might be the editor and you'll have someone coming along and saying this. And look, it's saturated. Yes. But because you're saying there's a variable here that doesn't exist before, it's not really a strong argument to say it's saturated, but it's interchangeable, right? Why this is a difference, why this is different to me, is that each of these covariances, literally you can come up with a function that says each of these turns into regression weights, regression coefficients. And you can just map them on, right? Up here. Whereas, if you're going to come up with a factor, that's like a brand new variable for people. That's putting a lot more, you think about just what happens in your field. If someone says, there's this new variable, it's called grit. Somebody look at grit. Oh, sorry, is that
Garbage.
there you go, right? If it's in this situation, you could say it's grit, or maybe it's just variation of the variables, right? They're identical. You can't say that, right? But when you call it grit, what happens?
You think about all those warm fuzzies about John Wayne.
You can talk about John Wayne. You can talk about oatmeal, or you think you're, something that's hearty. But no, the hard part is, I feel like that when you define a variable and everybody's like, oh my God, it's amazing, you sort of take science in a different direction, that's a worst thing to have happen, right? Because if it's not truly there, you have to be able to test whether it's there, right? So, and how do you test it? It's simple. You add the fourth item, right? This item, this model, has 1 degree of freedom. It might be 2. I can calculate it, right? There's 4, 5, so 24 times 4 plus 1 over 2, that makes 10. 14, there's 14 total parameters here. And then there would be 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12 model parameters. Should be 2 degrees of freedom there. And you should be able to test it. Not a strong test, but if you have a 4-item grit test, there you go. It's a little bit stronger argument to me than 3, right? So again, what am I saying? I've seen it be the case when you submit mediation analyses and get slammed because you didn't have model fit, when really it's sort of a meaningless statistic. And I've seen it be the case where there's a whole industry of those who teach SEM who say build 3-item indicator factors because they fit perfectly. And I also think that's BS. So you have to come up with a balance. That's why I'm going overboard on this. Okay. We good? Okay, you're gonna remember grit from this class, I bet. So Michael, I take it you're not into grit. I'm not putting you down or your work down when I start putting. Am I putting anyone else down? I just want to pick. Okay, I want to pick a topic. I don't want to have infighting.
Okay.
The scientific debate. Listen, I'm only picking up on buzzwords. If we could pick a trait that I could pick on that would offend nobody in this room. I don't care about the internet. Nobody in this room. Could you throw out some labels of traits?
It doesn't offend
Okay.
me. I just mean it's closely linked to a lot of the things we study.
Oh, well, I can understand like having that type of
Yeah.
resiliency, tenacity, like the things that I'm looking for adjectives to describe it. Yeah, absolutely, totally understand that. I'm more talking about like the next.
One would be satisfaction with life. There's a lot of issues with that one. Yeah.
Okay, I can pick on that one. That was the one that I learned all this with. There was a guy at Illinois at the time, Ed Diener, who was associated with it. And so his office was like across the hall from mine as a grad student and whatnot. So it's like, okay, I can pick on that. Now I'm guessing he's retired, maybe. I don't know. Anyway, point being, I'll pick on satisfaction with life. But what I'm trying to say is, you see what happened in research fields. Someone comes up with a new scale. It relates to a lot of things, and people start investigating it. And this process kind of reinvents itself. And there's going to be whatever, the satisfaction with life 20 years ago or 30 years ago, and grit today, there'll be the next one 5 years from now. And it's sort of how do you have a critical lens to discuss it from a statistical validation point, not just the validity of the actual term itself.
Yeah, I think that they made it, the grid people, I think they made a trademark.
Did they?
I
Yeah,
think,
they work at the University university or at
Yeah.
Stanford, right?
So it's
Not
not
surprised.
word. It's more like their research trademark, the word.
Yeah.
And
And in
I
that sense, it becomes really
Yeah.
easy to kind of laugh at.
Yeah,
Yeah.
the research
So-
commercialization part of the university is.
I think that's not what we associate.
Okay, no, and I'm
But,
talking
you
like
know,
I can
yeah.
see there's a, and this is sort of getting into factor analysis in general. There's a sort of list of synonyms that go
Yeah.
or that go with a factor, right? And whatever we call grit in your head that's triggering, that's like this and it's like this, like this. So I totally see on all those seem relevant, definitely. What I'm talking about is more the scientific process, right? So science, what we're trying to do is come up with, yes, there will be something that's also related to all those. Think of all the synonyms. Come up with another list of synonyms. There'll be another thing related to that, and there'll be a general word that gets applied to that in 10 years, and people will be really excited about it. It's like a repackaging of what happens. The part that we want to be really concerned about is whether or not we're providing good tests of hypothesis whether things are working.
But for those who want the trademark, whatever the
Yeah.
whatever the research tend to say, hey, we have.
That's right. Yeah,
I
the
think
business
that-
end.
Yeah.
The business end is just looking for anything that makes it look scientific because they think people will understand it, and that's what we try to teach here. Is try to teach understanding. Yeah, I mean, listen, research commercialization. I can't even get into that. It's sort of a smarmy feel. It has a smarmy feel to it, certainly, like a very kind of undercut science. But then I also look at like Stanford's doing pretty well as a university, but I look at the state universities, right? One of the parts that we get from KU, our KU Research and Innovation, or Research and Collaboration, whatever they're called these days, they are responsible to bring money to the university that we're not getting from the state. So, but by and large, I like the focus here is it's effectively things that are not. This is not as tangible as like a vaccine might be, right? Or a new way of extracting molecules from RNA or something like, something that would be molecularly based or otherwise manufacturable. I went to, they have these, used to have, I haven't paid attention in a couple of years, but they used to have, every month they'd have a series, just like an evening where you could show up over in West Campus and a bunch of inventors, faculty, and students would just give presentations on what they're trying to have patented. And it was mainly to try to get the community or people in Kansas City to think, hey, that would really help my business. Let me license with the university to try to use that. So it could be the case that people at Stanford are selling grit to, I don't know. But, it's where it comes from. And actually, on that note, where it really gets smarmy is as a student of the university believes it has a right to everything you produce as well. Right?
Blackboard, everything that we post is technically the university's.
It is, although the intellectual property policy of the university says that anything that you teach with is your possession.
Right.
So
you're protected, but we're not.
But if I put mine on Blackboard, once you use the Blackboard product, that's where you get screwed. But for me, that's part of the reason why I stay away from Blackboard altogether. Because I don't want anything to do with it. Now, of course, Google will go and say they could have the right to reproduce this. Absolutely, they do. But the university, from what I understand, won't stop me from that, from our agreements.
And then same thing with like the YouTube videos and stuff.
Well, the YouTube videos has a license, and actually you can select which types of license it is, but mostly I do the free whatever. But the license that you're granting Google is the right to reproduce the video, because people can share it or can just visit the website and people can see it. And you're not controlling that directly. And of course, once you put one video out there, anybody can take it and put it elsewhere. So I find this to be very interesting. The whole world of this stuff is just, sort of makes me as a scientist feel really bad, because it's like it's how the university makes funds to support the science, but there's sort of a mission creep, I feel like, to it. Is it really the case that you're gonna? And there are cases out there where undergraduates, sophomores at the university in some computer science or some engineering class have come up with something. The university says, "Thank you very much." It's like, yeah, that's right. It doesn't seem right that the student's paying the university to learn to get a degree, but now all of a sudden that happens too. But that's what the university will play. So yes, let's not make this about science ethics, all because of grit. I won't say grit. I'll just say satisfaction of life.
Yes.
I don't want to offend anybody here. I do understand the meaning for it, particularly in a lot of research contexts. I'm trying to, I get it. I just was more, not, that seems to be the latest, hottest word that it's come across my ears. I haven't, but there'll be another one, you know, coming up in 6 or 7 years, or maybe this year, who knows. Okay, more model fit. We talked a little bit about more model fit statistics before. This is going back to the analysis where we have not the saturated model, but this is with all of the data put together. Right? This is our model, our one-factor 6-item model. And here what we have are this set of statistics. These are testing global model fit. There's the standardized root mean squared residual at the bottom that tells you effectively, when I think of it, it's not exactly the case, but it's like an average distance of correlation. Right? That's where the standardized comes in. So standardized covariance is a correlation. So, wow, I don't know what that's doing. The root mean square error of approximation. So anyway, there's the word root here. There's the word root here. We want anything with a root in the title to be as low as possible. Think of it as roots are in the ground, like whenever you're growing trees or plants or stuff, right? So we want this, if this was 0, it'd be perfect fit. If the root mean square error of approximation were 0, it would be perfect fit. RMSEA is right here. It's an index of how far off we are per degree of freedom. Right? It's sort of an odd scale, though. Whenever you're not fitting, whenever you look at the null versus alternative model, there's this non-central chi-square that gets thrown into the alternative model, the discussion of statistics. And if you were in a undergrad, or if you took an ANOVA class and you were talking about power, sometimes you had to look at non-centrality tables for T or chi-square or something like this. The same thing shows up here. You don't need to contribute all that. What I'm trying to tell you is where this comes from is effectively how far off we are per degree of freedom. Standardized with it. And accepted practice in the world of the CFA biz is to think that RMSEA less than 0.05 means really good fit. What? Remember, before, to the statistician, if you got a significant p-value in your null alternative model, that's it. But to the world of social science and education, RMSEA is a big one. The neat thing about RMSEA is that it has a sampling distribution to it, so that we can come up with a confidence interval around it, and we can come up with a probability that that thing is under 0.05, right, from that sampling distribution. Here, 0.215 would be terrible fit. So when I'm saying that there is one factor that underlies these 6 items that talks about situational forgiveness, the data are saying, I don't think so. There's not one factor, okay, for the RMSEA. The same thing would be the SRMR, although some people say less than 0.08. I rarely even pay attention to this. Right? RMSEA is a big one. Now, alternatively, so RMSEA is an index that compares your model to the saturated model. Right? It's talking about how far off you are effectively per degree of freedom. It's a different scale than all that, but again, this is just in your head. You can think of it that way. The other statistics that we have, the confirmatory fit index and the Tucker-Lewis index, talk about user model versus baseline model. This talks about how much better you are. What was the baseline model? What was that? Independence. All the items were independent. So how much better you are than that model, which is a silly thing to compare to.
How much better you are?
Then the model where the covariance is set to be 0 for all the items. It's this one right here.
That one, okay.
Yeah. Right. Well, this will never happen in data. Right. So it's a silly one as well. But that's what these indices tell you. If you want the actual math for them,
So,
yes.
what did you say about
CFI and TLI are lumped together because they're various versions of your model versus the baseline model, the independence model. Shade it.
So I've often seen that CFI is reported in table zone. It's almost
Mhm.
recommended.
Yes, and that's fine. It is sort of a standard practice. The way I look at model fit now is as many good ones as you get, people are going to report.
Okay.
Right? So if you, RMSCA is almost standard,
Yeah.
and then whatever the CFI, TLI, or something else that makes it look good.
I'm gonna use that one. Okay.
It's not a hard science about it.
Okay.
But CFI is often reported, and the reason for that is if I go to M plus, actually I don't have all the M plus alpha, but M plus is a big program people use in this, and the three that popped out from M plus are RMSCA, CFI, TLI.
Yeah.
So you see, start seeing people.
Cremdo recommends RMSEA and CFI, and then confidence intervals, but then I haven't seen them use TLI.
No, I in the 1980s in psychometrics, in this club that I talk about,
Old guys know.
yeah, old white guy club. That was like that was like their deal, right? And there was like how you got there were people who are tenured based on how many goodness of statistics I think they could come up with, and there's a lot of them out there. There's a package in SAS that does CFA. It's called Calis, and there's one word option, and it spits out an entire, I kid you not, page of these things. I've never heard of them. This must be 40 statistics, right?
Just with model fit.
That's right. Just with model fit. And, each one of them has a different type of assumption and so forth. And then you get what I get, I don't know, there may be some, rationale statistically for why these might be better than others, but I see M plus just kind of report 3, and then all of a sudden I see the empirical scientists report 2 or 3, right?
Right.
So, honestly, if I'm giving you my stringent definition of this, I like the likelihood ratio test. I know that sounds terrible, but if you get that to fit, everything else is going to cooperate, right? The likelihood, yeah, the log likelihood. If you get that thing, this thing right here, this thing fits. You're in great shape. Everything else is going to work well. So I think I sort of remove myself. Everything else is sort of splitting over. Like, how bad is it, right?
So you would stop it if you have no significant differences between your model and the baseline.
That's right.
And the baseline model is it's a sequential analysis, sequential models.
Well, this is your model and the saturated model. The baseline has another one too.
Go further.
Yeah.
So kind of like standards for it then, like CFI, TLI, like
Bigger than 0.95.
Yeah, but what about likelihood? Like that's a little.
No p-value. A p-value that's not significant.
Go with that.
Well, I mean, you want to report that. You still have to report the other ones. But what I'm saying is, whenever this one works, the rest of them. There may be cases out there that you could probably dream up statistically, but in data, if this thing works, the rest are going to work. Jesse had a question on this.
Yeah. So it looks like Levon does the chi-square test for us.
Mhm.
And then on RMSEA, did you say that people generally want an RMSEA value?
They do.
Actual value?
They do.
Less than 0.05?
Less than 0.05 for the RMSEA.
Just happens to be 0.05.
Right.
Perhaps clarifying that was.
Bingo.
And this is good fit.
Great fit.
Great fit. But under
Where can you get by with? I've seen RMSEAs published with 0.11. The Basque, Randy Camphouse survey. I've seen the technical manual report an RMSEA of 0.18.
Yeah. The example from Cremdo is 0.108.
Mm-hmm. Yeah.
In their example.
So, I think practically speaking, you can be published. You can go get through the review process with terrible or relatively terrible fit. From my standard, for my own peace of mind, the better that likelihood ratio test looks, the better it gets. Now, I will say one thing. In the next few years, we're going to start redoing a little bit of this, so leave a little headspace for it. When we do Bayesian versions of SEM and CFA, we'll be able to quantify evidence for the saturated versus evidence for your model. And you'll be able to come up with right now we're in a no-win situation philosophically because you can never prove a null, right? So just means it didn't fit your model. But in a few years, when things become a little bit more understandable and prevalent, what we're going to see is there might be a Bayes factor there, or where they talk about kind of ratio of evidence towards one versus the other, or a Bayesian p-value that would say, I ran this lot longer estimation process, but I was able to see that my model was preferred 75% to the alternative. So there are going to be better statistics that we're about to get into that are a lot more mainstream. But for right now, unfortunately, I can't teach a whole class on that and have you function in the world that we're in. Ishi, did you have a question?
Could we talk a little bit more about the difference between baseline model and the saturated model?
Yes. The baseline model and the saturated model. So actually, there's a in the output. Let me get back to the output. So here is the actual output as it comes. There's this thing that says baseline test, model test baseline model. And again, just to remember what the baseline model is, here's what we have, right? So what we've learned at this point, that the likelihood ratio test that I'm concerned about is our model versus saturated. But that model test baseline model, so this part right here, model test baseline model, has 15 degrees of freedom. Right? Now remember, the saturated model had 27 parameters in this. Right? So that means, what is 15 here? The 15 degrees of freedom, that means there's 12 parameter difference between this, whatever this test is doing, and the saturated model. Or better yet, I didn't tell you saturated. Let's just testing the saturated model versus the baseline model. Skip ahead. Why do I say that? Okay, so this is to say, to provide evidence that your model fits, is the one we've talked about at this point. A lot of times it doesn't work. The next question is there anything to even be able to model in your data? So that baseline model is used most commonly, in my opinion, when I look at it, I use it to see whether or not there's a significant covariance that's different than zero. Are any of my covariances different from zero? Because what it's testing, when you compare the independence model with the saturated model, or the baseline model with the saturated model, you're effectively saying that none of these covariances is different from zero. Right? This is the null hypothesis. This is the alternative hypothesis. So if none of the covariances are equal to zero, what's that mean? Sorry, all the covariances are equal to zero. If you found this test to have a p-value that was very high, you didn't reject the null. You said the baseline model seems to be true. Because the factor loadings are formed from the covariances, if you have no covariances in your model, you should have no factor loadings. So you'd have no factor in the first place. So that's where that comes from. It's essentially let's just stop altogether, and do I even want to do any data analysis with this data set? Most of the time, in fact, I don't recall in my life ever seeing that be a non-zero p-value. I've heard a story from Lisa about there was a test of executive function she worked with some colleagues at Nebraska, and it was like the items were absolute, like no correlation whatsoever. Almost the part where there may have like been a coding error in the data that was like, wow, there's nothing, right? And so she said, yeah, there's no things that have zero correlation aren't factors, because there are what that correlation is meaning. What that correlation represents is the influence of the factor on the two variables. If it's zero, it's like saying there is no factor. Does that help us correct? Did you have yeah, okay. Other questions?
Can I just repeat what you said? Just
Please do, please.
So the independence model is the baseline, correct? Okay. And then we want to make sure that none of the covariances in the baseline model are equal to zero.
It's the opposite. It's if any one of those is non-zero, this should give you a p-value that's very small. Okay. Right? Because it's that like in ANOVA, that omnibus test where you're testing all the means simultaneously. What this model test baseline is doing is testing all the 15 covariances simultaneously that they're zero. If one of them is significantly different from 0, you should see this to be a significant test statistic.
So when you, what constraint to find what?
Right, but this is probably the most useless part of model fit output. If I'm going to rank model fit output for where my attention goes, like if you put the eye tracker on me and I'm looking at your data, right? My eye tracker goes to this, the test of your model versus the alternative. That's number 1. I'd go to RMSEA number 2. I'd go to CFI and TLI simultaneously tied for 3rd. I'd probably go to SRMR tied for 4th. And then I'd finally go to model test baseline model fit.
So, yeah, RMSE, and under that it says robust RMS.
Right, and that is just to give you where that comes from. The robust one's probably the one. Use the robust one. It's better. Where that's coming from is there's a chi-square difference between there's a model chi-square that comes from comparing your model to the saturated model, and that chi-square. Actually, I don't know. I actually don't know. Let me just back up. This is the chi-square formed with the likelihood ratio test. Oh no, that didn't. Oh no, I'm sorry. The likelihood ratio test in the robust column. That first one was the chi-square of. What did I just do? Okay, rerun it at least. Hang on here. Sorry, everybody. And ridicule me as being this terrible person. So this right here, that's the robust rescaled likelihood ratio test. That chi-square gets used in this test statistic right here. I don't know what that's doing.
Oh, okay.
And I'm not sure where that robustness is coming from. So I need to know. I need to look that up. I'm sorry. I'll look that up or do the best I can and try to give you some information on that.
So just to confirm, maximum likelihood, RMSEA, CFI, TLI, and whatever else.
Yeah, that's it.
So you get to the model base, whatever.
Mm-hmm.
If nothing like 1 through 4th one do not give you any information, like
That's right. A
model test
where-
baseline model.
That's
model
right.
test, yeah.
Yeah, if I'm getting down to this, there's one other case where I would look at it. Right? This is the odd case that again may happen once in your career. Right? But if this p-value was non-zero, all those things were good. Right? If you have zeros, exactly zeros in your covariance matrix, that means all your factor loadings are exactly 0. So that also means, let's see here, this is the saturated model, right? So when this is the saturated model, what happens to all your model fit statistics? They look really, really good. You have great model fit, right? It is possible the case that you have perfect model fit and everything's equal to 0. All the parameters are equal to 0.
One more question.
Yeah.
So is one of the parameter or the model fit indices that we don't typically want to use NNFI?
And
That's an N plus one.
yeah, that's an N+1. I don't see that very often. Honestly, if you report everything that comes out from the statistics that you're using, you'll be fine, right? What typically happens is people only report the ones that look good, right? I feel like, right? If you go, we have a big push for replicatable analyses and research. So like if you're putting all your stuff, submitting your script and everything with it where people can see the output, light of day, put them all down. It's fine.
And then are we going to talk about what constraint tenable means?
What do you mean by that?
It's something that comes out in N plus that if it's like differs from 0, and then it's yes or no.
I don't know the answer to that. Let me look it up.
Okay.
Good, right?
Yeah, I have a question about the CFI value.
Mhm.
So you said the CFI is how much value your model compared with the baseline model, but the value on your output
here's what's happening to compute the CFI. It's 1 minus the maximum of chi-square minus degrees of freedom for your model versus 0 over the maximum of the null model, which is the baseline model, or 0. Right? And so when that happens, right, what happens is when your model fits much better than the baseline model, the max is the same in both of these ratios, and so then it just becomes 1. So it's an absolute index. You don't have to say.
For absolute base, the value of CFI should be 1.
That's right. For the TLI, it is possible to get values bigger than 1 because they're not using that maximum function. Right? It's possible to because what it happens to be is this comparison of chi-squared to degrees of freedom. Nobody wants that to be bigger than 1. When it becomes bigger than 1, you start to see people in my shoes go, yeah, it can be. It usually means something else is wrong with the data or the analysis. Like the data are really, really weird. So, but is this a little bit helpful description? So, long story short, when you're trying to show your model fits, for me, you want the likelihood ratio test, the RMSEA, the CFI TLI if you want to put the NNFI or whatever your other favorite goes after that, right? Then comes standardized root mean squared residual. Right, that's sort of my order of importance.
But CIs with the RMSEA.
Would be great, but I don't see it a whole lot. But you know.
And usually 90% confidence interval?
Yeah, that's what sort for whatever reason because it comes out of M plus. So I think in Levon you might be able to tweak the option to get it a different one.
And I think at M plus you can't do. I think you can tell at 95.
Oh, okay. So yeah, we're splitting the difference of like terrible fit. I think that's what we're getting at, right? Like that's why I don't like. I think for me, again, I'm more trained in the stat world. So when I see that p-value, you say no, they're different.
Yeah.
All right. Yeah. Like how much different? Well. Nobody really knows what's enough because there's all different ways of like kind of quantifying what different happens to be, right? So what happens if your model doesn't fit? Let me ask you that.
You could try and make modification indices to see if you can approach acceptable.
That's what we're about to do, yeah.
So
We get into that, right. But let's imagine you take it and you get it published. With bad fit. What's it mean for what goes on with what you do? Why is fit so important?
I think it's telling like it depends on the fit of index that you are using. It will tell like for the one RSM, like the one that will measure the difference between the correlation of the predicted and the actual.
Well, yeah, but let's just put it this way. Let's just say it's bad. Bad fit. Let's just all agree. RMSEA, who cares? Like, pick your favorite statistic. It's terrible at it, right? What's it mean for your results?
Unbalanced results.
Right. So let's talk a little bit about why real quick. Why this matters. Let's go back to this crazy matrix equation here, right? This is what the covariance matrix is given by the CFA model, right? It's this weird combination of loadings, factor variances, and unique variances, right? So if you want to play around with things, just to see how things work, if you fix all the loadings to be equal, right, and you set the factor variance to 1, what you've effectively done is take this off-diagonal term where it's loading times factor variance times loading, and if it's one factor model, let's just call it one factor, right? You've set all of these effectively to be the same term. Where they're the same term, what the model is going to do, the most likely solution is effectively the average of what should be there, right? That means the things that were low are going to get pulled up to high to be in the average. Things that are high are going to get pushed down to low. And that means what's happening is that the factor loading itself, the number that goes there, is either stretched or squished, but you don't know. Right? It becomes biased. But if the factor loading is biased, you also know the unique variance is going to be biased because the factor loading plays a role in trying to come up with what the item variances happen to be. All right, okay, so factor loadings are biased. What happens? Factor loadings are biased, unique variance is biased. That's the actual point estimate. Not to mention the validity of the standard errors of the estimates, because the standard errors of the estimates assume the model is true. Most likely you think you have far less error than you truly have. Right? So this is biased. The unique variance, which I don't have up here, is biased. Standard errors are biased. Okay, so now that means you can't tell whether or not this loading is significantly different. Or it can't accurately tell whether that significantly measures, the item significantly measures the factor. That sounds kind of bad in building your scale. But think about, I haven't gotten there yet, but what goes into the score that you most want to give people? Right? Well, wouldn't you know, factor loadings and the variances. So if the model doesn't fit, not only can you not do anything good with figuring out what structure your items actually fall on, if you try to go and get people factor scores from it, they're going to be biased too. Not only they're going to be biased, you're also going to think they're way more reliable than they actually are. And so there's two sides to this. Can I give you the cynical? I'll give you the optimistic. The optimistic is, this is why I'm so concerned about model fit, is that the better we can, the more evidence we can establish for model fit, the less likely any of that's to be true. The more precision we get with our loadings or our unique variances, because what we end up doing with a lot of what we do in measurement, I like the factor scores, they're better. The biased version of me says this. One of the problems we have that is seldom discussed with this replicability crisis, where we can't repeat it in their studies, is that model fit is not good enough for this. That's one of my arguments, I think. Model fit's not good enough. Because when that happens, we think we got great reliability. This also goes to your classical test theory. Because what happens, I can show you, and actually in the bottom of the next few classes, I can show you how we can get coefficient alpha out of our factor loadings. Right? It's actually a very constrained version of a model. Right? So we can do a CFA model that spits out alpha, the same that if we could just go plug our data into whatever an SPSS and give us alpha, and they're the same number, right? So if that's the case, and this model is a CFA model, then everything that I just said about CFA applies. And if it doesn't fit, alpha's not accurate. There's the problem, right? So my argument about why model fit is so important is everything that we do with measurement involves fit. It assumes fit is true. If fit is not true, we're in trouble. We are opening ourselves up to issues with replication. Now, for those of you who don't have a PhD yet, and who are in a spot where you would like to have a research career, what that means is it's a lot harder to get things published if you're worried about this. Because if you can get things published where you just add stuff up, show an alpha, there's no model fit involved. In fact, alpha is model fit, right? So this whole process takes time, effort, energy, and whatever else. So the cynic in me says, I totally get why people do it, or ignore this, because it's a lot easier if not.
And if you get published,
Well, that's sort of the ultimate goal for a lot of people, because we all need to eat, right? We all want to have a paycheck. We all want to have what we do. That being said, if you're really concerned about the science, you're not sort of buying your own marketing campaign, then model fit has to be the standard, right? The better you can do for model fit, the more likely it is what you're saying is going to be accurate.
do you have an article that you would suggest kind of as like an exemplary article for this?
Let me ask Lisa. Lisa probably has one. My problem is I usually, when I read articles, they're on the methods side of things. I don't usually see, it's like a throwaway data analysis that doesn't really tell us much. But basically, an exemplary version of how a person in an applied study.
Exactly.
Absolutely, I will try to find one for you.
Great.
Is it possible that the model fit is poor, but all the factor loading are significant?
Yes, in fact, that's actually commonly the case. when model fit is poor, what we often see is it takes a lot for a factor loading to be non-significant. Usually what happens is you have a lot of other loadings that are significant. So you sort of have a stable base for the factor itself. There's a lot of items and maybe one or two items that don't show it. But when model fit's poor, depending on which direction your model is misfitting, usually it's the factor loadings are being stretched too big, biased upwardly, and because of that, it makes it look like they're bigger than they really should be. So that's my anecdotal, not supported by data claim. Right? So pretty much everything I say, I'm pretty sure you can find a counter example for, by the way. So just know that. But I'm building my argument. I'm trying to build my argument based on philosophical underpinnings. Hopefully you believe them. Don't buy everything I'm selling. And don't buy everything everybody else is selling either. Let's just put it that way. Like science, right? This is, make this. What's that?
So just don't buy anything.
Nope. No, I mean you have to. It's like let the buyer beware, right? You have to sort of. You have to be very critical about it. I think that's what I'd like you to be. I mean, we're talking about this class, as I mentioned, this is about validation of a different type. That means really got to put a critical lens on it as much as you can. Okay, so what happens is we take a look at model fit. We take a look, and it doesn't fit very well. So that's what we call global model fit. Right? Global model fit. That's all of the indices. It's the likelihood ratio test. It's what pops out first. It's global because they're one number summaries of the entire fit. And really what we're talking about is where this misfit's coming is the covariance matrix, right? So that each individual covariance, we can get down to that level and see how far off we are from it, right? So that's the next step. Figure out where locally the model is not doing so well. So the word strain shows up. I don't like that one either. I guess it's sort of like I can see that in cooking, right? We strain things, but I'm thinking of it as like lifting or whatever else. It's not good. What we're going to do is we're going to go and output. I even showed that example to you. We're going to go output a version of what the model thought the covariance matrix should be versus what the covariance matrix was. Right? So again, going back here, here's the covariance matrix in the data. And then if we don't have one here, but there's a covariance matrix the model is giving. We're going to take we can take the difference between the two. And we can see, hey, there's some big numbers away from zero here, right? So that's a fairly easy way to do it. That's what we call, sometimes we call that a discrepancy. More often than not, we call it a residual. It's not that residual, right? It's this model fit residual. I like to call it discrepancy matrix because of that. There's so many other words of residual. It's how far off our model's covariance matrix is from the data's covariance matrix. Now, that matrix, when we just take the direct subtraction of the covariances, remember that the covariances are like correlations with scale, meaning the size of the variance of each variable going into it matters, right? If you're looking at I talked about height and weight before. If you're going with inch pounds versus foot pounds, the covariances are going to be at different scales. So there are different versions of these residualized or discrepancies. One is called a normalized, which basically takes the difference and tries to divide by some type of standard error of the difference, giving you what looks like to be a z-score. Right, so now everything's on the same type of scale, and we're going to get into that next time.
Leave us on hanging.
I keep telling you, you don't have to come back, but I promise. And I'll even go so far as to say there's no quiz next time.
That's great.
Okay? So you don't have to be forced to come to class. But I want to make it worth your while to be here. I even told you they don't believe what I'm saying, about trust but verify or something like that, like let the buyer beware. But no, I'm happy to, if you want to come up with a criticism of what I'm saying, please do bring it to me. I'd love to hear it. I may be wrong, number one, but I also love to have a chance to argue a case too. So. All right, everybody, thank you. Have a great Tuesday and Wednesday, and I will see you Thursday. Just 1 second.